Okay, so we found that for a perfectly insulated system, an adiabatic system, that there's a nice simple relationship between P and V. Just like with an isothermal system where you have P times V is a constant, for an adiabatic system where no heat is exchanged, it's only internal energy changes due to the work, you have PV to the gamma is equal constant. And so because you have this nice analytic curve, function of P with respect to V, you can analytically figure out what the work done by or on the gas is, because this P is a nice function of V. So that's what we're going to try to do today. We're going to try a little mini lecture. We're going to try to figure out the work under here, and we're going to find that that's a very useful thing later on in the course. Okay, so by saying PV to the gamma is a constant, nice thing is any point along that curve, P and V, as long as it's P times V to the gamma. So if you have an initial point, an initial condition, PV initial, then P initial, V initial to the gamma is your constant. And instead of just saying P is inversely proportional to 1 over V to the gamma, you can say P is equal to P initial, V initial to the gamma over any later V to the gamma. And you can take this term and plug it in for P in that page, and you get this. Okay, the integral of V initial to V final of P initial, V initial to the gamma over V to the gamma dV is the work by the gas. Term on top, because it is constant, it only depends on your initial conditions, and bring that outside of the integral right there, like that, and you get that. And so it becomes a very, very simple integral. You can look it up in a table if you don't know it by heart. It's the integral of 1 over x to the n. In this case, instead of x, we use v, and instead of n, we use gamma. And so evaluated, that should say v initial to v final. Okay, from v final to v initial of this. Okay, so it's the initial condition, v initial to the gamma, times 1 over 1 minus gamma v to the 1 minus gamma. Okay. So what you can do is you have to plug in v final here, and then plug in v initial and subtract that off, and then you multiply by p initial, v initial to the gamma, and you get this messy looking thing. So you should try to do this on a piece of paper, right? You know, try to get the steps between this and this. I skipped a step here, but you should be able to get from one place to the other. The next thing we're going to do is we're going to say, well, look, I know that P initial, V initial to the gamma is also equal to P final, V final to the gamma. So I'm going to substitute this term here with P final, V final to the gamma, because it will make it easier for me to collect terms. And so I have P final, V final to the gamma, which is going to be the same. And so when I do that, then I can collect my V's together, because this V final, you know, is V to the gamma times V final to the 1 minus gamma. The gammas basically cancel out. Same thing here with my P initial, V initial to the gamma. This gamma is subtracted off by that gamma, and you end up with this very, very simple relationship. The work done by a gas in an adiabatic process is this: P final, V final minus P initial, V initial over 1 minus gamma. That is nice and simple. Now, of course, the work done on the gas is going to be negative of that. Okay, so as you'd imagine, if V final is greater than V initial, this would be a positive number, which would mean that the work done by the gas is positive, which makes sense in an expansion, because in an expansion you are doing work, the gas is doing work. On the other hand, if V final is greater than V initial, then the work done on the gas would be negative of this, okay, because it would be negative work done on the gas. The gas is doing work, which is the opposite of work done on the gas. Okay, so this is the work done for an adiabatic process, the work by the gas in the adiabatic process. And for an ideal gas, gamma is equal to 5/3. Okay, so we figured that out previously. We showed that from the derivation of PV to the gamma is constant, that gamma for an ideal gas is 5/3. Recall another process we talked about earlier, and that was the isothermal process, where the work done by the gas for an isothermal process, okay, is nKT natural log of V final, V initial. Okay, so you have two very, very helpful analytic ways of finding work done by a gas. We're going to find that that's extremely useful for analyzing something called the Carnot engine in the next chapter, which talks about the second law of thermodynamics. Okay. So the next topic we're going to talk about is equipartition of energy. Basically, how energy is divvied up in when you add temperature. Okay, where does the energy go? Okay, so if you remember back when we were talking about a fixed volume process, for a fixed volume process, it was like the can over the Bunsen burner that was closed, and basically all you were doing was heating it, and the only thing you were doing to the gas was heating. So there was no expansion, there was no contraction, it was a fixed volume, and therefore the only change in internal energy was the heat. Okay, so for a fixed volume process, your delta V is 0, and so your first law tells you that the internal energy is only about the heat. Okay, fixed volume process is only about the heat, and so therefore you have the difference in internal energy is 3/2 nk delta T. All right, we figured that out. This is true for an ideal gas. Okay, this is true for an ideal gas. So that means that the change in temperature, okay, the change in temperature is the heat over 3/2 nk. All right, so that's remember we had 3/2 R was the molar heat capacity, 3/2 K would have been the per molecule heat capacity. And for an ideal gas, this is exactly what is found. This is experimentally verified for monatomic gases like helium, argon, neon, things like that. Funny thing is, when you do experiments to figure out the heat capacity at constant volume of a diatomic gas, like air, for example, which is a mixture of oxygen and nitrogen, O2 and N2, or if you do an experiment on hydrogen, which is also a diatomic gas, you don't get delta T is Q over 3/2 nk. You get delta T is Q over 5/2 nk. And that's a bit unusual. So how do we explain that? Well, the thing is, a diatomic gas has two atoms on the end of a molecular bond. Okay, we can think of it almost like a baton, where the atoms are the ends of the baton, and then the baton itself, the stick in the middle, is the intermolecular bond between the two. And so, for a diatomic gas, in addition to being able to move in 3 dimensions, to have a velocity in z, it also is able to rotate. Okay, so let's take a look at a picture like a rotating baton. I want you to just look at the first picture. Let's not worry about the second picture or the third picture. They're actually somewhat misleading. But let's say we have a baton that is aligned with the z-axis. Okay, at least initially. So it could rotate this way around x, or it could rotate this way around the y-axis. Okay, so we can twirl it around the y-axis, we can twirl it around the z-axis, and that's another place for it to put its kinetic energy. It can rotate in either of those 2 degrees of freedom. On the other hand, if you rotate it around the z-axis, around the length of the baton, in other words, if you just like spin the baton like a spiral of a football, because the baton is so thin, because atoms are so tiny, you basically don't have any rotational inertia. You don't have any moment of inertia around that z-axis. And because of that, you really can't rotate it in that direction at all. It just doesn't take any of the energy. Okay, so basically a rotating baton has 2 extra degrees of freedom. The rolling does nothing. Okay, rolling it along the z-axis does nothing. Okay, a regular single atom has 3 degrees of freedom. It can move back and forth. It can move up and down, and it can move, for better lack of a better thing, to and fro. Okay, and so there's 3 possible directions of translational motion. There's 3 degrees of translational freedom and 2 degrees of rotational freedom for a baton. So here is your nice diatomic molecule, and let's not worry about this because we're not going to talk about that. So rolling does nothing, so it's essentially 0, and you have 2 or more places to put 2 more places. This should be 2 more places to put the energy when you heat it up. Okay, and so for a diatomic gas like air, you put that in the can and it doesn't seem to heat up as fast, and that's because the energy doesn't just go into translational motion, it also goes into rotational motion. Okay, it turns out that 1/2 kT of energy, okay, remember why temperature doesn't increase as fast, as I said, but it turns out that 1/2 kT of energy goes into each dimension or degree of freedom for the diatomic molecule. And so for every translational degree of freedom, you get 1/2 kT, so that adds up to 3/2 kT. That's why a monatomic gas has 3/2 kT as its internal energy. Okay, but for a rotational baton, you have another 2 degrees of freedom, and so you have another 2/2 kT, or a total of 5/2 kT as the possible degrees of freedom. Okay, so the equipartition theorem basically just says in equilibrium there's an average energy of 1/2 kT associated with each degree of freedom. And for monatomic ideal gas, you have 3/2 kT. For a diatomic gas, you have 5/2 kT. There's supposed to be a K in there. Sorry about that. 5/2 kT. So again, in a diatomic gas, there's more places to put the energy when you add the heat, so the temperature rises more slowly. And we're also going to see that this is going to change the heat capacity. Okay, the heat capacity for a monatomic gas, your heat capacity at constant volume, was 5/2 R, right? For a diatomic gas, that CV is 7/2 R. Okay, so this is going to end up changing your gamma as well. For a monatomic gas, the gamma was 5/3. Okay, your gamma was 5/3. Okay, for a diatomic gas, it's going to be 7/2 over 5/2. Okay, because the heat capacity at constant pressure is also going to be 2 dimensions bigger. So your gamma is going to be equal to 7/5. So that's going to be different as well. Okay, we're almost up against our 15-minute time limit, so we're going to stop right here, and we'll talk about the second law of thermodynamics next time.